Okay. If there seems to be no questions, let's start on an entirely new topic. Okay, not an entirely new topic, but a new branch of quantum mechanics in a way. These are so today what we are going to talk about primarily are time dependent problems. Of course, you have already learned part of this in your earlier courses. Of course, all of you know this, that time dependence is governed by this equation, the so-called Schrodinger equation. This is the actual Schrodinger equation. And I'm pretty sure all of you have also seen this, that if H is time independent, then, and if H psi is E psi, that is, if psi happens to be an energy eigenstate, then psi of t is going to be e to the power minus I by h cross et psi at t0, psi at t minus t0, psi t0. Or so this is the special case if H is if psi is an energy eigenstate. For a general psi also, the basic rule is for the special case when the Hamiltonian is time independent, psi of t is simply given by e to the power minus I by h cross h t minus t0 psi at t0. So the upper line is the special case when you start with an energy eigenstate, and if your initial initial state is an energy eigenstate, then you just pick up a phase factor. If not, you can always find out the evolved time evolved wave function just by applying this operator e to the minus I by h cross h t minus t0 on the initial state. So this much I'm pretty sure everybody knows. The question is, what happens if h depends on time? Has this already been covered in your earlier courses? By the way, what I have already said has been covered, right? Yes? Okay. So Shayan, this yes is about what has already been done. But what about psi of t when h depends on time? Have you solved such problems before?
No, sir.
Okay. Now, of course, Hamiltonians which are time independent form a very large part of the physical world. And so whatever we have done here, that is this general relationship, is actually quite important. However, there are of course situations where the Hamiltonian might depend on time. In fact, there's one very important situation where we have to consider this, and that's the following. So let me just go back a bit and let's go back to history a bit. When Bohr first talked about quantum theory, he had some ad hoc principles, but basically what he was trying to do is resolve a conflict between classical electrodynamics, which said that an electron going round a nucleus must radiate energy all the time, because any accelerated charge would radiate energy and would then fall into the nucleus in almost no time at all. That is, atoms simply could not be stable under classical physics. So Bohr solved this by essentially postulating two things. He postulated stationary states and he postulated quantum chunks. That is, he said, with some rather involved reasoning, he just didn't write the equation down from just out of the top of his head, but from some rather convoluted reasoning, he managed to say that states in which the angular momentum were integer multiples of h bar would not radiate energy. So these would be stationary orbits. But then, if that of course solved the problem of stability. The atom would then be stable simply because of this forceful statement that atoms, when the electrons obey those particular quantum relationships, then they will not radiate energy, and so they will stay stable. However, atoms do radiate energy and do produce light. And to explain that, he had to also incorporate in his theory the basic idea that electrons would jump from one energy level to another spontaneously or for some other reason, whatever. And when an electron jumps from a higher energy level to a lower energy level, the energy difference will be radiated as a photon. Okay. So this was basically a couple of ad hoc statements which he had made, which ended up giving him the power to explain spectra, in particular hydrogen spectrum, perfectly well. However, of course, when quantum mechanics came in proper, then Schrodinger actually managed to show the stationary H psi equal to E psi, whatever state actually obeys this, these are stationary states. And why are they stationary states? Because according to quantum mechanics proper, a state which obeys this, of course, obeys the relationship I wrote down a while ago, that the state does change with time, but it changes with time just by picking up a phase factor, and an overall phase factor does not have any bearing on the physical properties of the system. So the properties of the system will not change with time. So quantum mechanics, in particular Schrodinger's equation, managed to explain stationary states perfectly well. But now comes the second problem, because now this is not ad hoc. This is in the very nature of quantum mechanics, that Hamiltonian eigenstates will be energy eigenstates. So the question now would be, then how would you get transitions at all? If a system is in a stationary state, how would you at all ever consider the electron as something which jumps from one state to another? So what are your ideas about that? Why are there transitions at all? Yes? If you really believe quantum mechanics, wouldn't you be saying that the system stays in the same state forever? The Sharon is saying the Hamiltonian is time dependent. That's one way of getting the answer. Actually, that's really not the precise way. The very precise statement is something else. But at least for many purposes, you can treat the Hamiltonian as time dependent. Why? Because you can think of, say, external radiation interacting with the electron, and therefore giving it a potential which depends on time. Now, why am I saying that this is not exactly accurate? Can anybody tell me that? That is, why am I saying that treating this problem as one with a Hamiltonian which is time dependent? That is exactly what is done. But why am I saying that this is not exactly accurate? Can anybody explain that? Yes? Well, if this picture were exactly accurate, then one very common phenomenon would never have occurred. Can anybody tell me what? Hint, I'm talking of a phenomenon which is associated with spectra or with transitions between energy levels. you have a Hamiltonian which describes the interaction of the electron with the nucleus, right? So that is time independent. The picture that we are trying to use here, at least the picture that suggests why transition can occur, is that there is external radiation, and because there's external radiation, that radiation has electric fields, and the electric fields interact with the charges, and because the electric field in external radiation is time dependent, you end up with a time dependent part in the Hamiltonian. And so, strictly speaking, this initial assumption that the Hamiltonian is time independent is not perfectly true. Now, there's one kind of phenomenon which can never be explained by a picture like this. Can anybody tell me what that is? Something which happens to electrons in atoms, which simply cannot be explained away this way. So when you have transitions, what kind of transitions can there be? All of you know the nomenclature here, right? There are different kinds of transitions which are possible. So what kind of transitions are possible? You have simulated absorption or emission, right? This is what happens when external light either causes an electron to go up in energy, that's the absorption, or come down in energy, that's the emission. Here, absorption and emission, of course, is with respect to the light being produced. So simulated absorption and emission can be explained by this. What cannot be explained at all by this picture is something called spontaneous. If this picture were perfectly accurate, then if you had an electron in highly excited state in a completely dark room, then the electron would stay in that completely excited state forever. That highly excited state forever, because now that there is no external disturbance, there will be no way in which that electron can come down in energy, because that down Hamiltonian is no longer time dependent. Okay? So spontaneous emission actually requires a slightly deeper explanation. We are going to come to that when we talk in more detail about simulated absorption, emission, and the spontaneous case. Okay, but this is something I would like you to bear in mind. The spontaneous emission simply cannot be explained away just by saying that the Hamiltonian really is time dependent. Because in the case of spontaneous emission, it simply isn't. Okay. Now, in these cases, what we do is we typically assume that the Hamiltonian has a large part which is time independent, and hopefully a part which we know how to solve. On top of that, you have a small time dependent extra perturbation term. And now what you have to do is use time dependent perturbation theory to try to understand how things will evolve in time. In particular, the kind of questions we are really interested in is, if you have the system originally in some state, what is the probability of finding it in some other state as time evolves? Of course, if you started in an energy eigenstate, the probability of finding it in another energy eigenstate at a later time would have been zero if the Hamiltonian had been time independent. So the perturbation term actually produces the probability, non-zero probability sometimes, for a transition. And that also is very important because it tells you how bright a spectral line, for example, will be. Because, of course, if a particular transition has high probability of occurring, it will produce more photons, simply because there are many atoms available. So just a high probability will translate to a larger number of photons, so a brighter spectral line. So all these questions fall under the ambit of time-dependent perturbation theory, which is our last major approximation technique that we are going to study. So far, all the approximation techniques we have studied, the Rayleigh-Schrodinger perturbation theory, variational method, or WKB, they have essentially focused on solving H psi equal to E psi. That is the equation for the time independent Schrodinger equation, which is actually important in solving even the time dependent Schrodinger equation, but only if the Hamiltonian is time independent. For time dependent Hamiltonian, H psi equal to E psi has no such immediate connotation. So this is what we are going to study in the next part of the course, time dependent perturbation theory. But today what I'm going to do is I'm going to talk about something which is closely related to time dependent perturbation theory, but which can be done independent of it. This is also a time dependent problem, and it's a very important time dependent problem nowadays, especially because of many nice consequences which come out of it. So this is basically a situation where we talk about adiabatic changes in a quantum system. And the name adiabatic here simply means slow changes. So that's essentially what it means. So the connection between this and the term adiabatic in thermodynamics does exist, but that connection is rather complicated. So let's not worry too much about why this is called adiabatic. To us, adiabatic essentially means a situation where you are very slowly changing, where you have things changing with time, but changing very, very slowly. When I say things, I mean the Hamiltonian of the system changes very slowly with time. Okay, so this adiabatic systems, or the corresponding theorem, a very important theorem that we are going to talk about today, the Adiabatic Theorem, and some consequences like something which you may have also already heard of. Have you heard of the Berry phase by any chance? Geometric phases, Berry phases. Anybody? Okay, you may not have, but it so happens that Berry phases are things which come in naturally in this context. But nowadays, these are things which are used in many other much more advanced subjects. So I'm not going to, of course, deal with everything that topological phases or geometric phases in quantum mechanics are useful for. I'm just going to give you a basic indication of how they come into the theory. But these are actually matters of contemporary research. So it's one of the more advanced things that we are going to talk about in this course. The adiabatic theorem itself has been around for a long, long time, but some of its consequences we are still finding out nowadays, very recently. So this is what we are going to talk about, basically a situation. Let's start with a situation where the Hamiltonian H of a system depends on a bunch of parameters. So these parameters could be anything. I'm just keeping it abstract at this stage. So there are n parameters on which your Hamiltonian may depend, and so we are going to simply use a shortcut. We are going to write this H R vector, and of course, and for any particular set R of vector parameters R, that is R1, R2, Rn, HR is a Hermitian operator, and it has a complete set of eigenstates. So basically what we are looking at is this. We have energy Hamiltonian eigenstates. Okay, we are not going to call them energy eigenstates any longer, because that particular interpretation may not really work very well here. But in general, if the Hamiltonian depends on a bunch of parameters, then for a given set of values for that parameter, that's a fixed Hermitian operator. It has energy Hamiltonian eigenvectors, so, and also corresponding eigenvalues. So this is what you expect, that of course the eigenvalues would depend on the parameters, because the Hamiltonian itself does depend on the parameters. And because these are eigenvectors for Hermitian operators, you expect the standard properties that they form a complete orthonormal set. So this should be the identity, and now you might very well say, what's new about this? All I've done is I've just put in an extra label on the Hamiltonian, and you have said H is labeled by a bunch of parameters. But other than that, whatever I've said is something you knew all along. That H is a Hermitian operator, it has a spectrum, eigenvalues and eigenkets, and eigenkets form a complete set, an orthonormal set, and so on. That's exactly what you have done here. Okay. Now, there are several issues, of course, even before we go on to talk about a more complicated situation. Even here, there are several issues, like if there's degeneracy in a particular energy eigenvalue, then phi-n's, of course, are not uniquely known. You can always take any linear combination of whatever you are calling phi-n's to be your phi-n's. That's one issue. Degeneracy will, of course, make unique labeling of the eigenvectors just by the energy eigenvalues impossible. You will need further labels. Other than that, given a phi n r, even if En were not degenerate, would phi n r be unique? Suppose En were non-degenerate, the energy eigenvalue or the Hamiltonian eigenvalue here. What would phi n r? Can phi n r be changed despite that? Yes. Can you even in a non-degenerate eigenvalue, is the eigenvector unique? Yeah, the point is you can always change the eigenvector by an arbitrary complex phase. Okay, so there's a question of phase choice that can be made. Now, this is going to be very important later on. While the phase choice is perfectly arbitrary, you can make them once and for all. And the basic idea is you will have to make to ensure the states are single valued in parameter space. That is, for each given r and a fixed n, there is exactly one phi n r. Two different phi n r's do not coincide. So that's all we are saying. We are saying that for a given parameter set of bunch of parameters, for a given n, I will choose my choose my complex phase in such a way that I will not end up choosing, say, two distinct phases for the same state. This is okay. How can that become an issue? We will talk about that later. Okay. But for the timing, this is something which we usually take for granted anyway. So, frankly, we don't even think about such issues most of the time. You will see later that you will have to think about such issues in the kind of problems we are going to deal with. But that's for later. Now, the reason why I'm saying all this in context of time-dependent Hamiltonians is that this parameter vector, r vector, which of course is r1, r2, rn, could be time-dependent. And what will this do? If the parameters change with time, parameters which define the Hamiltonian changes with time, then this leads to time-dependent Hamiltonian. Okay? The question that we have now is, in such a situation that the Hamiltonian is time dependent through the fact that the parameters which describe it are time dependent, which is usually why Hamiltonians are time dependent in the first place, is it possible for us to write something like this? Does this make sense? Does this equation make sense? Is it possible for us to find eigenvectors and eigenvalues for the Hamiltonian at a particular time t? You've earlier found that if the Hamiltonian is time independent, you can always find a complete set of eigenvectors and so on. Just hold on. Let's open the. Okay, sorry, I'm back now. So the question was, is it possible to at all solve this, write an equation like this? Now that you have a time-dependent Hamiltonian? In other words, time-dependent Hamiltonians, do they have energy? Do they have eigenvalues and eigenvectors? Yes. Tell me. If you think that there is no reason why they can't have eigenvalues and eigenvectors, tell me that. That's fine. No, that all I'm really saying is just this. I'm saying H, the Hamiltonian. If you just strip off the RT, all this is really saying is something like this. This, of course, makes perfect sense when the Hamiltonian is time independent. When the Hamiltonian is time dependent, does this make sense? Can we at all have eigenvectors and eigenvalues?
Sir, for a specific t,
Yeah.
we can have eigenvalues and eigenvectors.
Right.
But if we change the t, then the eigenvalues can change, may change. But
Usually they would change, right?
uh,
Yeah. So the
but
point
then
is, okay. So I guess the point, the usually there's some confusion about this simply because people tend to always associate Hamiltonian with time evolution. If you just forget about that for the time being, you just think of the Hamiltonian as some operator. At a particular value of t, it has some value. Of course, the value will change with time, but at a particular value of time, there is some particular value for the Hamiltonian operator. It's a Hermitian operator. It, of course, has a complete set of eigenstates and eigenvalues. The only point would be something like this. When you have this equation for time independent Hamiltonian, then you know that if the system is in phi n at time t0, then at a later time t will still be in the state phi n. The only thing that will change is that it will pick up a phase factor. Now that connotation is no longer true now. Okay, that is the only thing that has really changed. What you have is that you have instantaneous Hamiltonian eigenstates and instantaneous Hamiltonian eigenvalues. H of R of t is called the instantaneous Hamiltonian. It's a value which the Hamiltonian takes at a particular instant of time. So the instantaneous Hamiltonian at time t, that is a Hermitian operator, has a complete set of eigenstates which obey all the properties that you would want eigenstates to have. So that is phi n R of t, phi m again R of t at the same time is definitely delta mn, and phi n R t ket phi n RT, bra phi n RT will be summed over all n will be the identity. Okay, so these are instantaneous eigenkets and eigenvalues. The ENs are the eigenvalues. The only thing is, what we now can state clearly is this: if so if at time t0 the system is in what happens to be the one of the instantaneous eigenstates of the Hamiltonian operator at time t0, then in general at time t greater than t0, so this is the deviation from stationarity basically. If the Hamiltonian had been time independent, then energy eigenstates are stationary states. Once you're in there, you stay in there forever, as long as the Hamiltonian really is time independent. Here we have time dependent Hamiltonians, and so this, if the system is in an instantaneous energy eigenstate at some instant of time, at a later instant of time, it will not in general be in the same eigenstate. I'm not talking about whether it picks up a phase factor or not. Point is, it will usually not be in the same state even when you take into account the phase factors. Okay, so this is what we expect anyway. The Adiabatic theorem actually, in a way, is just a contradiction to this, in a sense. Well, the contradiction really is something like this. The statement of the Adiabatic theorem goes somewhat like this: if the system so these are called energy eigenstates or Hamiltonian eigenstates, depending on which book you are reading, but basically these do not have the same connotation as in the time independent case, but still the nomenclature is just instantaneous energy eigenstates. Isn't an instantaneous energy eigenstate one of them? So the original statement, the statement I made just now, it starts exactly the same way. If the system is in the instantaneous energy eigenstate phi I r t0 at t equal to t0, of course, this is the new thing, and the variation okay, then let me make a loose statement now first. Then the loose statement is the system stays in the same instantaneous energy eigenstate. Of course, not that at time t0, but that at time t. So if you were in the ith energy eigenstate at time t0, as time evolves, you stay in the ith energy eigenstate in time t. Let me stress at this stage the state at time t, the ith energy eigenstate at time t could be a very different state from the ith energy eigenstate at time t0 simply because the Hamiltonian has changed. So its ith energy eigenstate, of course, also has changed. But what we are saying here is the system stays, once it was in the ith energy eigenstate to start with, and if the Hamiltonian varies sufficiently slowly, this is where the adiabatic part of the adiabatic theorem comes in, then loosely speaking, the system stays in that particular ith energy eigenstate, but of course at the time t. Any questions so far?
Sir,
Yeah.
what do we mean by ith state?
So the energy. So we are assuming for the time being, just for simplicity, that the Hamiltonian is a discrete spectrum. That is, the energy eigenvalues are discrete, right? So once you assume that, then it's pretty easy. The 0th state is the ground state. The 1th state is the next energy eigenstate, and so on.
Okay.
Okay. So you just go by the ordering of the energy eigenvalues. So ith state is the ith one in ascending order. Starting count is count starting from 0 or whatever you want. Is that okay?
Yes, sir.
Okay, let me make this statement, of course, is a loose statement. So let's make it more precise. What happens if degeneracy breaks if there was degeneracy? That's not really a very important question for this, really. What's more important is what happens if degeneracy occurs during time evolution. That actually becomes very important, as we will soon see when we look at the proof of this. Okay, let me just state this correctly first. This is, of course, a very loose version of the statement. The actual statement would be something like this. So forget this thing. Start from then. The state time t, which is bigger than t0, that is for some later time t, differs once again. When I say energy eigenstate, I mean instantaneous. And what is more important is this, and the difference sufficiently slow. So what this means is, first of all, if your Hamiltonian varies slowly with time, we are of course going to make this more quantitative soon, but if your Hamiltonian varies very slowly with time, then the actual energy, actual state which phi I r t0 will evolve into will differ from the corresponding energy eigenstate phi I r t by a very small amount, number one. More importantly, you can make this difference as small as you want just by making the variation in the Hamiltonian slow enough. So this is the adiabatic theorem. Okay, the adiabatic theorem really starts here. It's a rather long statement. It starts here, and this was a loose version of way of saying this, you would just drop this whole thing. If the system is in an instantaneous energy eigenstate phi I r t0 at t equal t0, and the variation of the Hamiltonian with time is sufficiently slow, then the state at time t differs from the corresponding instantaneous energy eigenstate phi I r t by a very small extent. Okay, to be by. And more importantly, you can make the difference between the state at time t and phi I r t as small as you want simply by making the variation of h sufficiently slow. This is what the Adiabatic theorem states. Okay. Of course, this is a theorem, so it means that this requires a proof. So what we are saying is the actual state at time t, of course, must satisfy Schrodinger's equation. I mean, the time-dependent Schrodinger equation. And a solution to the time-dependent Schrodinger equation will be very, very close to phi I r t. So the system will essentially track the instantaneous energy eigenstate as the Hamiltonian changes. Now this, remember, happens only when the variation of h is sufficiently slow. Okay. Are you with me so far? Any questions about this? I'm going to give you the proof of this soon, but are there any questions about the statement? Okay, so since this may sound a bit abstract, let me give you an example to begin with. Let's talk about a very, very simple Hamiltonian, a simple time-dependent Hamiltonian. Let's say just a two-level Hamiltonian, something which you have done two-level systems before, right? Things like spin half or things like that. Yes? Have you done that? You have done spin half, right? Okay, fine. So this is a two-level system. You can think of it as a spin half system, but with a small twist. This is a time-dependent Hamiltonian. It's a Hamiltonian which is proportional to the time. In fact, you can easily recognize that apart from this alpha by 2 factor into t, the rest of this matrix is simply sigma 3, right? The sigma or sigma z, the Pauli matrix. Okay. So can anybody tell me what are the instantaneous energy eigenstates and eigenvalues? This is what we find out from the fact that h of t at any given t, for any value of the time, h of t is a Hermitian operator, in this case a Hermitian matrix, and you can easily find out its eigenvalues and eigenvectors. So can anybody tell me what the eigenvectors are at time t? Yes? They're simple 2 by 2 matrix. Tell me what the eigenvectors are. And this is one of the simplest ones, which I'm pretty sure you all know the answer. After all, this is a diagonal matrix, right? So the eigenvectors should be trivial. Yes? Come on, this is something which is the kind of question which you should kick yourself for not being able to answer, if you are not really able to answer this one. The 2 by 2 matrix, so of course it should have two eigenvalues and two eigenvectors. So eigenvalue 1 What's that? Come on, this is a diagonal matrix, right? The diagonal elements should be the eigenvalues. And what about the eigenvector corresponding to this one?
Rajrupa has answered the question in chat box.
Oh, sorry, I missed out the chat bubble. Yeah, 1, 0. Okay, Raju had already given the answer. 1, 0 and 0, 1, alpha t by 2. Plus minus alpha t by 2. Okay, I think that's what you wrote. I can't, my eyesight is bad enough. I can't, sorry, I didn't see that answer. Okay, so these are the instantaneous eigenvalues and eigenvectors of the Hamiltonian. But can anybody tell me what is going to be the state? Suppose I start at the state 1, 0 at time t. At time t0, let's say. What will the state be at time t? That is, what will the solution to this equation be at time t? In this case, psi is just a two-component vector, right? So the Schrodinger equation simply is this. That is what all the time-dependent Schrodinger equation really is. So what does it tell you? It gives you two equations, right? It gives you IH cross del psi 1 del t. The top component is alpha t by 2 psi 1, and IH cross del psi 2 del t. The lower component is minus alpha t by 2 psi 2. So this immediately tells me what psi 1 and psi 2 are going to be, right? So remember at t equal to 0, let's say at time 0, t equal to 0, you had 1, 0. At t equal to 0, you had psi 1 equal to 1 and psi 2 equal to 0. So what is the solution to this set of differential equations given this initial condition? At time t, what is psi 1 going to be? It's easier to say what is psi 2 going to be at time t. What is psi 2 going to be? And let me keep this chat box on so that I can see. What is psi 2 going to be at time 0? At time t? No, given that at time t equal to 0, it was 0. Psi 2, of course, is going to be 0. You're starting from 0. And psi 1 is simply going to be e to the power minus, as Shaun is saying correctly, it's simple, just integrate. T dt integral is t square by 2. That's all you have used, and use the initial conditions as well. So basically, at time t0, you had this. At t equal to 0, you had this. At time t, psi of t is simply given by this quantity. So apart from the phase factor, e to the power minus I alpha t square by 4h cross, which is an overall phase you can always pick up. Apart from that, you started at the state 1, 0. You are staying at the state 1, 0 forever. Okay? Yeah? The state doesn't change. It just picks up a phase factor. Apart from that, in this particular one-dimensional problem, particular simple two-dimensional time-dependent problem, you have a very, very simple solution. Once 1, 0, forever 1, 0. 1, 0, 1, forever 0, 1. So now comes the actual question. Say, by the way, it doesn't have to be at t equal to 0. This could be at t equal to some large negative time, let's say. Of course, if this were initial condition were given at some time t0, then this formula will only change slightly. This expression will simply change to t minus t0 whole square here instead of t square. That's all. It's pretty straightforward to figure out that is going to be the case. So the question I have for you is this consistent with what Adiabatic Theorem says? The Adiabatic Theorem is exactly what I told you a while ago. If the Hamiltonian changes sufficiently slowly, then if you are in an instantaneous, in the ith instantaneous energy eigenstate at time t0, you will stay very, very close to the ith instantaneous energy eigenstate at time t. So this result that we had worked out for this very simple special Hamiltonian, this is of course a very, very simple Hamiltonian, but for this simple special Hamiltonian, we have found out explicitly what psi1 and psi2 are, that is what exactly psi of t is. And it's telling me that if you start at 1, 0 at time t0, maybe some large negative time even, then for later times t, you are going to stay in state 1, 0 exactly. Overall phase factor doesn't change the nature of the state. The chance probability of it going into the other state is exactly 0. Question is this consistent with the Adiabatic theorem? Isn't this exactly what Adiabatic theorem told us? Okay, how many energy levels does this have? 2 energy levels, E1 and E2. Which one is lower? If I label the energy eigenvalues in ascending order, E1 will be the smaller one, right? Which one of the two is E1? Is this one E1 or this one E1? Is the number, the one on up here plus alpha by 2t, is that E1 or is this E1? Okay, and the answer is, of course, here there's a catch. As Shaun is saying, which one is E1 actually depends on time here. In the sense that when t is negative, then this one is actually higher. So for negative t, this is E1. And the moment t switches sign, goes from negative to positive, this one becomes E1. This is what t greater than 0. Right? So so Adiabatic theorem would have actually told you exactly the opposite of what would have happened here. If you really were to, this looks like this theorem, this particular situation where you have an exact solution available, seems to actually fit the adiabatic theorem. You start at 1, 0, you stay at 1, 0. But what you must realize is that 1, 0 actually was the lower energy level for for any negative time. But for positive time, it actually is not the lower energy level, it's a higher energy level. And what that means is that adiabatic theorem would have told you if you start at some time, some large negative time at 1, 0, for large positive time you should actually have gone to 0, 1. Because for large positive time, 0, 1 is actually the energy eigenstate, the lower energy eigenstate. Okay? So what we see here is a direct contradiction to what the theorem that we just stated, right? So this seems to be a very sorry state of affairs. We just stated a theorem and then given exactly solvable answer, a solvable system, and for that exactly solvable system, we thought that the theorem was actually working out, and it turns out that it doesn't. It actually is a complete violation. Now, there is a reason why this is a complete violation. So, in order to understand that, we of course have to go back to the proof of the adiabatic theorem. In particular, we have to look at exactly what it means when you say H is sufficiently slow. Okay, of course, that's a vague statement as of now. So, until we prove the theorem, we will not really be in a position to understand what this sufficiently small means there. Okay. So, any questions so far? Let me just draw a picture, and this might make it easier to understand. Although with my drawing skills, it might even make it more difficult to understand. But let's say if you have time along this axis and energy drawn along this axis, then what happens is the lower energy level so E1 essentially goes like this, and E2, the higher energy level, actually goes like this. So the one marked in blue is E1, the one marked in red is E2. And notice that E2 actually was alpha t by 2, was minus alpha t by 2 for negative times and plus alpha t by 2 for positive times. Whereas E1, on the other hand, was alpha t by 2 for negative times and minus alpha t by 2 for positive times. So if you start with 1, 0, and if this is the instantaneous energy eigenstate for large negative time, the instantaneous energy eigenstate corresponding to E1 at large positive times is actually 0, 1. Whereas 0, 1 was the energy eigenstate E2 corresponding to E2 at negative times. At positive times, it's 1, 0. So adiabatic theorem would have actually told you that 1, 0 should have gone to 0, 1 as time goes by. But the exact solution tells you exactly the opposite. It tells you that if you are starting at 1, 0, it stays at 1, 0 through forever. Picks up a phase factor, but stays 1, 0 forever. And that solution is so simple that there is no chance of our having made a mistake there. So basically, this particular example that we have picked up happens to be one in which the adiabatic theorem is violated strongly. And in order to see why, we need to actually take a look at how the proof of the adiabatic theorem really goes. Then you will see exactly where that particular proof would fail for this particular case. Okay. So now let's try to prove adiabatic theorem. And for that, of course, what we need to do is start with this. This is what we need to solve, or at least this is the system, the basic equation that we need to satisfy at all times, right? And we are given that at time t0, psi t0 is actually one of the instantaneous energy eigenstates of H, that is phi I, the ith, at R of t0. The only problem with writing this expression out is that there are many brackets which you have to open and close, so I have to be careful about that. Other than that, this is pretty straightforward. All you're saying at time t0, there's a particular set of bunch of parameters that fixes the Hamiltonian at time t0. You have an ith energy eigenstate corresponding to the energy eigenvalue, instantaneous energy eigenvalue of EI. Now, of course, the question that we have is, what is psi t? But we can always do this, right? We can always write psi t in this form. Claim we can always write this. And why can we always write this? Yes? Why is it that we can always write this? Now, the answer is simply because H is a Hermitian operator, actually a self-adjoint operator, and has a complete spectrum at any given instant of time. So phi and RT are eigenstates. They form a complete set. So any state, leave alone the state at time t, but in each and every state can actually be written down as a linear combination of these states. The coefficients Cn, I put a tilde on top simply because later on I'm going to modify the definition, change Cn tilde into something else. And that is why in anticipation I'm writing this as Cn tilde, so that the later coefficients, the one we will directly deal with, are the ones we are going to call Cn. So of course what we do next is simply take this expression, phi t, and plug it in here into the Schrodinger equation. That's all you need to do. So what you get that's simply what I get when I differentiate this expression. Cn tilde, of course, will in general depend on time. So Cn tilde dot plus another term. That's the left-hand side of the Schrodinger equation. The right-hand side will simply be sum over n Cn tilde. Left-hand side, of course, has the Hamiltonian operator going and hitting psi t. But when H hits this psi t, it merely jumps across the sum, and the linear coefficient just goes and hits this. And since these are eigenstates of H of t, you are going to get En so this is nothing. This is just the Schrodinger equation rewritten in terms of these basis vectors. Or if I just move this side, all these phi and RT terms in one side, what you get is sum over n Cn tilde dot minus I plus I by h cross En So I've just moved this term to the other side. That's simply equal to sum over n. So these are the equations that you have to actually handle. Now, how many equations are these? The answer, of course, is infinitely many, as there are eigenkets of H. And they're all coupled together in this. So the easy way to decouple them is to realize that these after all are a Cn tilde is missing with En. Yeah, you're right. I should have a Cn tilde here. Perfect. Yes. Cn tilde dot, this came from differentiating Cn. This, of course, came in from the Hamiltonian acting on the other side. So there was, in the previous step, yeah, I had Cn tilde, I had to move that on the side. Okay. So if you just hit both sides by phi n r of t, use the fact that the instantaneous Hamiltonian is a Hermitian Hamiltonian like any other. So it has a complete orthonormal basis. So I just hit with this bra, and this automatically gives you delta mn here, right? Because these are just numbers. So what you're going to get is Cm dot plus I by h cross En Cm simply because of the delta mn has given me a Cm here. Okay, so that's what you get from the left hand side here. Oops, by hitting with this bra. On the right hand side, of course, what you get is not so simple. On the right hand side, what you get is simply equal to minus sum over all n Cn tilde Okay, so this is now, of course, still a couple set of differential equations. This is an equation for a particular m, and you have one equation for each allowed value of m, so infinitely many such equations, of course. But on the right hand side, you have a sum over all possible n, so that is infinitely many terms on the right hand side. So it's still rather complicated looking, to say the least. But if you see an expression like this somewhere, x dot plus some function of t x, what is the obvious thing you should do? So if you have differential equation looking like this, x dot plus f of t into x equal to something, let's say some function of t, how would you solve this? Suppose the right hand side was some known function of time. Can you solve this equation? Okay, let me just write it out in full, then perhaps it will strike you. Do you know how to solve this equation? Our equation is not exactly of that form because this thing is not a known function of time as yet. But at least the left hand side is of this form, right? Derivative of a variable plus some function of the independent variable times x. So how would you solve an equation like this?
By multiplying an integral factor.
Yeah, this is exactly how you, one of the standard things that you learn in differential equations, one of the first things you learn actually, the integrating factor technique, right? You have to multiply by an integrating factor. And what would the integrating factor be? Come on, everybody knows this, right? First year, or even class 12.
Exponential of integration of f.
Yeah, in e to the power integral of f of t prime dt prime, right? So what you could do is actually multiply both sides by this integrating factor. And in anticipation of that, and in fact, that is the reason why I wrote a tilde here, because after you multiply everything by an integrating factor, what I'm going to get is what I'm going to actually call the Cn. Time t is equal to the I by is Cn tilde at time t is the I by h cross integral So because we anticipated this this form of the differential equation that I will need an integrating factor here, I actually put this in the tilde in so that I can now deal with CNT without the tildes. So let me just try to write down the actual equation which CNs will obey. That is, for this, of course, you have to multiply both sides by e to the power I by h cross integral from t0 t of em rt prime dt prime. And if you do that, the left hand side will simply become okay, but there will be something here, won't there? What factor will be sitting here? Well, remember what you had to do to get this into this integrating factor thing is multiply this thing by e to the power I by h cross em rt prime dt prime. Whereas in Cn tilde, when you go over from Cn tilde to Cn, what you have multiplied by is e to the power I by h cross en rt prime dt prime. So there's a mismatch between the two factors on the two sides. So what you will end up with is e to the power I by h cross okay, just because for lack of space, I'm not writing em of r of t, I'm just writing en of t. So this is the differential equation which each of the coefficients obey. Now, why are we so interested in this? We are interested because our situation is this, that at the initial time, at t0, Cm t0 was simply delta mi, right? Our system was precisely in the ith instantaneous energy and state. So Cm t0 was 1 only if m were 1, m were I, 0 otherwise. So initially everything on the almost all of these coefficients were 0, only one of them was 1. And now we are trying to find out how this evolves in time, and we have got a differential equation for this. And our claim is going to be is this, that if m is not equal to I, then even at later times t, Cmt is going to stay very, very small. That is exactly what the Adiabatic theorem tells us. But what we have got here is dgt of Cm is some expression, some rather complicated looking expression. From this, how can we at all conclude that Cm at a later time t is going to stay very small? That is the question. So, in order to get there, firstly, we need to sort of handle this question. What exactly is this quantity? This is what we are really doing is, I'm taking del t of phi n RT, the rate at which the nth energy eigenstate changes, and hitting that with the bra phi m RT, right? So to understand what this is going to be, let's start with the defining equation for this. So the defining equation, of course, would be so because this is always valid, this is the defining equation for the phi m's. If I differentiate both sides of this with respect to t, that will give me a rate at which del m and del RT is going to change. So this is going to give me h. Just change one. So left hand side will give me two terms actually. One where del t goes and acts on this, and the other when del t goes and acts on h. So you get plus. Sorry. That is, of course, the left hand side. What about the right hand side? That gives you del En del t. This is just simple differentiation. The next obvious step to use would be, well, this is an equation between two kets, but numbers are much easier to handle. And how do you get numbers out of kets? You just hit them with the bars, right? That's how you get numbers. So if you hit both sides by, say, the bra phi n, what's going to happen is, so you're hitting with bra phi n on both sides at r of instantaneous bra phi n. So when bra phi n hits the h, that of course gives you En RT out. I'm just shortening my notation a bit. I'm not writing R of t here because you all know that there is an R of t here. Sorry. Okay. And what does this equal? This equals okay. So now at least one result here should be pretty familiar to most of you. I don't know whether you have already seen this before. You should have. The special case where m equals n. When m is equal to n, what happens is this term and this term cancels out, right? That is when m equals n. And then, of course, delta mn is just 1. So what you get is del En del t is the expectation value of del h del t in the nth instantaneous eigenstate. Have you seen? This is sort of an obvious kind of looking result, but it's really rather a non-trivial result. Have you seen this before? This particular result? It's a theorem. It's named after two physicists, one of whom is rather famous. Have you seen this before? The rate at which the time-dependent Hamiltonian's energy eigenstate, instantaneous energy eigenstate changes, is actually the expectation value of del H del T. Now, this is the Feynman-Hellman theorem. I think Hellman is spelled with a single M. So have you been exposed to this before in your course? The Feynman-Hellman theorem? Has this been taught? Okay, no, fine. So this is an important theorem actually for time-dependent systems. So it's an important thing to know. Okay. But what happens when m is not equal to n? When m is not equal to n, this term drops out because delta mn gives you 0. And notice phi n del t phi m is exactly the kind of stuff that we have sitting here on the right hand side of our equation. Here you have phi m del t phi n, but fine, that's just interchanging m and n will give you that. So here, this kind of overlap, phi n del t phi m is there both on both sides. So it's easy to see that ultimately what you get is this. So if you differ derivative of phi m's overlap with phi n, works out to be nothing but so the n-mth matrix element of the operator del H del T. But that's not enough. Then you divide by em minus en. Right? So this is in fact what we managed to do is derive two very important results about time-dependent Hamiltonians on one go. The m equal to n case gave us the Feynman-Hellman theorem, which actually is very, very useful. We will use it several times later. And the other one is going to be very useful for the proof of the Adiabatic theorem, which is what this quantity on the right-hand side of this equation really is. This quantity. So once you take that into account, our differential equation ends up looking like this. So the equation that we had was this one, rather formidable looking. Now I have got an expression for this, which makes it begin to look slightly better. But then the equation will still look basically like this. Let me make some space. Because evaluated with the parameter is RT. Okay, the only difference between this and this are the m and n have been interchanged, but that's because in the equation you get phi m del t phi n times exponential of Okay, so is this perfectly correct? Actually, there's one term which is wrong here. Can anybody see that? Okay, maybe it's a bit too complicated to see in one go. So what we have done is taken this equation. Let's copy this equation out. So this was your original equation, the one below. And using this phi n del del t phi m's expression as del h del t nm by em minus en, I've rewritten this expression into this one. So have I done this thing correctly? Of course, there's one mistake which you can immediately see. That's another obvious mistake. That's this sum of course should be over n and not over m. M is a fixed index on this side. So can anybody spot one term at least which is wrong there, or at least one missing term? If you just look at this expression, just this one. Yeah, the point is this n, of course, cannot be correct for this particular formula cannot work for n equal to m, right? But this sum n is over all n. So actually, there's one term in this sum, the n equal to m term, which is missing, which this equation will not tell me exactly. Why? Simply because when we tried this is the equation that we had, but if you try deriving phi n del del t phi n using this, it will simply give you 0 equal to 0. Both sides will cancel. And putting n equal to m in this equation gave us the Feynman-Hellman theorem. But it told us it is nothing about phi n del del t phi n because that just dropped out of both sides. So the point is this equation is almost correct except for one more piece, which is I don't really know what happened to the special term when n equals m. Of course, when n equals m, what you will have is this. You must so have one more term here, minus Cm t times gamma t, where gamma is real. So I will, okay, gamma, which of course may very well depend on m. Okay, so you should realize what I have done here. I have just said that I do not know what will sit in front of CMT here because I have no way of writing that in terms of the things that I already know. But one thing I actually know, which is I know that this quantity, when the term for n equal to n is simply going to be, this term is going to go away because this is going to be simply 1. You will get Cm here, and you get phi m RT del del t phi m RT. Okay. This is something I cannot find out from this equation that we had derived. But one thing we can find out directly, which is this. This has to be purely imaginary. And how can I prove that? Any ideas? And that's what I've done. I've just said that, okay, it's minus CMT into something, and that something has to be a purely imaginary thing. So I wrote it that as I gamma mt, where gamma m is a real function of time. But how do I know this? That phi m del del t phi m is purely imaginary? I'll just give you a hint. This follows immediately from the properties that we know of the phi m's. Very straightforward. Okay, it actually follows immediately from this. How much is this? Yes? This of course is 1, right? So, and if you differentiate both sides with respect to time, what you get is phi m del t phi m, the thing that we were looking for, plus del t phi m, whatever this bra is, but you should realize that this and this, these two terms are actually adjoints of each other, complex conjugates of each other. So what this equation is really telling you is that the real part of this, which is this thing plus its complex conjugate by 2, is 0. So it's purely imaginary. That's all we really know at this stage. Okay. So now, the important question at this stage is, what are the approximations that we made in deriving this differential equation for CMT? Yes? We started from the Schrodinger equation. And in getting to this equation, what kind of approximations have we made so far? Yes? So if you have been paying attention, you would be able to tell me what approximations have been made here. Okay, let me tell you what approximations have been made here. The answer is none. This is exact. We made no approximations. We started with the Schrodinger equation. We just rewrote it in a different basis. That's it. And all these steps that we have taken in the throughout, they're not approximations. They're exact steps. So far, no approximations. Now we will make approximations corresponding to very slowly changing Hamiltonian. So far we have made no such assumption. This equation would be valid. The equation I've written down right now would be valid irrespective of whether the Hamiltonian changes fast or slow or whatever. Okay. But now comes the point that I'm assuming that the Hamiltonian is changing very, very slowly with time. If that is true, del H del T is small. Okay. Now, what exactly does it mean when you say a dimensional quantity is small? We will sort of fix soon. But if you assume that this is small, notice that this thing is a phase factor, right? Because it's a phase factor, it has a magnitude of the order 1. So in any way, this will not be a large quantity. This thing is small. So what we expect is that basically Cm dot is going to be pretty close to the initial value. Remember, the initial value of Cm at T0 is simply delta Mi. So notice that if m is not equal to I, initially you had 0 value for the Cm's. So the approximation, that is the first approximation we can immediately make, is something like this. We can say that if m is not equal to I, then in this entire sum, I can replace all the Cn's by the initial values, and then this simplifies a lot. Then, by the way, because we're talking about m is not equal to I, the initial value of CMT is 0. So I don't care about the fact that I don't know what gamma m really is. It just goes away. So Cm dot at time t is at least approximately equal to what? So what should I write this as? Approximately? What we expect is Cn's, which were zeros to begin with, will change with time, but will change with time in proportion to delta delta, because that's the rate of change. So actually Cn's will be like delta delta also. So basically you will end up with delta delta whole square, second order in delta delta. If we ignore that, if we want to keep only terms which are first order in delta delta, what will the right hand side become? Notice that initially all the Cn's were 0. So the rate of change, because that has a delta delta in it, at a later time t, whatever its value will be proportional to delta delta. That is, however much it changes from its value at t equal to t0, that will become proportional to delta delta. So basically, these terms will actually contribute to second order in delta delta. So if you want to keep only first order in delta delta, since delta delta is taken to be small in the adiabatic approximation, what do you expect here? What should the right hand side be like? Will there be any term left on the right hand side? Once you want to keep first order in delta delta only? Once again, let me stress this. At first glance, it may look like all the terms are going to survive because they're all first order in delta delta. But note that the CNT themselves have a rate of change which is first order in delta delta. So CNT themselves will be first order in delta delta at time t in general. So there's only one term that will survive if you keep only terms up to first order. Which one is that? Will any term survive at all? Or will you just get 0? Of course, if you just got 0 on the right hand side, then you could say all the CMs will stay 0 if they are not equal to m is not equal to I. So system will stay in the ith state. Adiabatic theorem has been proven. But that is rather, that is going to land us in all kinds of trouble, because we just saw a case where adiabatic theorem does not work. So there must be some limitations to this. There's only one term which will survive on the right hand side, and that's actually pretty straightforward. I claim that all the CNTs are of the order of delta delta, except for one of them, which is remember we are putting going to replace all of them by the initial values roughly. So well, there's only one Cn which is large even at the initial time, so you don't have to worry about the fact it changes to the order delta delta. It has already a large value which is n equal to I. So the only term which will actually contribute to first order in delta delta is actually the term where n is equal to I, where of course CIT is just 1. So this is going to be approximately so this is now we have made an approximation. Until now everything was exact. But this is the basic approximation which allows us to talk about the adiabatic theorem. Now, well, now since all the Cm dots change very slowly with time, all we can do is we can replace all of them with the initial values. That's what we have really done here. And on the right hand side, there is actually only one term which can actually change rapidly with respect to time, right? If you look at the right hand side now, you have del H del T, which has to be a slowly changing function of time. EIEM, remember, changes with time, but since the Hamiltonian is a slowly changing function of time, then EIEM also will change slowly with time. So all these terms change slowly with time. Okay. So is there any term here which changes rapidly with time? On the right hand side? There are just three terms, right? There's only del H del T, then there's EI minus EM, then there's this phase factor. I'm claiming that the Hamiltonian is changing slowly with time, so EI, EM, all these energy eigenvalues are also changing slowly with time. So is there anything in this expression at all which changes rapidly with time? Or does not change slowly with time? Yes? Well, it's pretty obvious. This one, EM minus EI may change slowly with time, but EM minus EI could be large. Large changing slowly with time, depending on how big the gap between the energy levels are. Okay? And because EM minus EI may be a large value, this quantity essentially is EM minus EI into T minus T0, as long as you are assuming EM minus EI is changing slowly. So exponential of that is could be a rapidly changing phase. So basically, every term here is slowly changing, although these all change with time. They are at time t, but only this term changes rapidly with time. All the others are slowly changing with time at this stage. So what you can do is rewrite this as approximately again. Things will change slowly with time. We just put their initial values there at RT0. The term which changes rapidly with time, that's the only term for which this is EI minus EM at RT0 into T minus T0. But now I have an expression for Cm dot T which is very easy to solve. So integrate this. So to get CMT and show, okay, so this is your final homework. Now that you can integrate this over time explicitly, this is a pretty straightforward thing to integrate. Once you integrate this and find out an explicit expression, from that try to argue that the adiabatic theorem will work as long as a particular condition is obeyed. And the condition, let me just write down the condition, which is what you would have to prove. The condition for the adiabatic theorem to work is this. Evaluated at the initial time t0 is much less than 1. If this is correct, if this condition holds, this is exactly what we mean when we say slowly changing with a certain time. If this condition holds, you can show after you do the integration. The integration is trivial. And after you do the integration, you just need a small amount of work to come to this conclusion that CMT will stay very close to 0. And in fact, can be made as close to 0 as you want by making del H del T small enough. By essentially, if this condition stays much less than 1, if this quantity. Okay, so that's the proof of the adiabatic theorem. And let me just quickly tell you why it did not work in our example that we had. The exactly solved example that we had at energy levels which went like this. This was E1. This one was E2. This is E2. So at t equal to 0, what we have is this situation that E1 and E2 come up very, very close to each other. In fact, as at t equal to 0, E1 and E2 coincide, which means this condition, which essentially controls what is the probability that the system will go into the state M if it were in state I. This quantity can no longer be treated as a small quantity. It will no longer be much, much less than 1 because this denominator will vanish at t equal to 0. So because here you have level crossing, or at least you have a degeneracy as time evolves, you suddenly end up with this kind of a situation that for this particular problem, at least the adiabatic theorem's conditions fail. So adiabatic theorem does not work. We will follow up on this and try to find out a bit more non-trivial problem which we can still solve exactly and see explicitly the condition under which adiabatic theorem would work there. And then we will go on to talk about Berry phases from this. Okay, that's all for today. And as I have said already, I think everybody got the mail. This Friday being Good Friday, we will not have the test this Friday. We'll have it next Friday. Of course, that also means that all these things are going to go into the test. The further the test is delayed, of course, you have more material to cover. But that's only a price you have to pay. Okay. If there are no questions, I will just wind up today. It seems that there are no questions.